fait plaisir d'accueillir le professeur Liu, Bing Liu de l'Université d'Illinois à Montréal, soi-disant à Montréal. Il va nous parler, son thème est d'atteindre la précision limite en apprentissage continu. Qui a lu son, d'ici, qui a lu son résumé? Et est-ce que c'était en français ou en anglais? Encore, pardon? Anglais. Alors, je raconte quand même en français. La capacité d'apprendre en continu et d'accumuler des connaissances tout au long de la vie est une caractéristique fondamentale de l'intelligence humaine. Cependant, cette attitude essentielle est absente des paradigmes actuels de l'apprentissage automatique. Cette présentation explore l'apprentissage continu en apprentissage automatique en mettant l'accent sur les défis de l'oubli catastrophique et de la séparation intertâches des classes. Ces problèmes ont empêché les méthodes existantes d'atteindre la limite théorique de performance, souvent avec un écart assez significatif. Les travaux récents montrent qu'il est possible d'atteindre cette limite, apportant des perspectives fascinantes sur la cognition et les fondements de l'intelligence artificielle. I just told them your summary, although they've all seen it. Now I'm going to give a little bio, and then I will pass it to you. Professeur Liu, le professeur distingué et titulaire de la chaire Peter L. Deborah K. Wexler. Is that the name of the chair, Peter
Wexler, yes.
Okay. En informatique à l'Université d'Illinois à Chicago. Il a obtenu son doctorat à l'Université d'Édimbourg. Who did you work with at Edinburgh when you took your doctorate?
Austin Tate.
Ses recherches actuelles portent sur l'apprentissage continu, où tout au long de la vie, les systèmes de dialogue en apprentissage continu, l'analyse des sentiments, l'apprentissage automatique et le traitement du langage naturel. Il est l'auteur de plusieurs ouvrages sur ces sujets et a également reçu de nombreuses récompenses Test of Time pour ses articles de recherche. Comme j'ai dit à professeur Bing, j'ai posé vos questions, 18 parmi vous, vous avez soumis des questions, j'ai posé ces questions à GPT pour voir ce qu'il répondrait à vos questions et ensuite ce que lui prédit le professeur Liu va répondre. I already told Professor Liu about that part. So with that, I've chattered enough. The title of the talk is Achieving Upper Bound Accuracy in Continual Learning. And I present, and Professor Liu welcomes questions during his presentation. I'll be mediating and letting him know when there's a question. Otherwise, it's all yours, Professor Liu.
Yeah. All right. Thank you for the invitation and also thank you for the introduction. So my talk today is going to be about this particular title, Achieving Upper Bound Accuracy. Obviously, this was a very difficult problem to achieve this accuracy. And now we think it's possible to do that. Why is not moving?
Well, we should have tried that.
No, my computer is not moving. Oh, okay. No, it's okay. All right. So here are the basically the topics. I will talk about I will introduce continual learning and also some key challenges. And then I'll discuss a little bit of theory about one particular type of continual learning, which is called class incremental learning, which is probably the most challenging sort of setting of continual learning. And then I will discuss some sort of CRL using in-context learning. Essentially, this is using large language models. Then I will talk about how to achieve the upper bound accuracy, and which is very sort of interesting and also quite unexpected. And it's very simple. And then after that, I will discuss some sort of possible implications or some my thoughts about AI and possibly about learning as well. But they are going to be somehow controversial, possibly. And after that, I will talk about how do you extend sort of traditional continuing learning to open world. Essentially, we are basically talking about the world which is that's unknown stuff in the world. I got some cold. I got a quite bad cold, and so my voice is not great. So lifelong learning, or now people call continual learning more often. It's essentially invented in 1996, 1995, that time period. But between that and then 2014 or something like 2013, 2014, there was not much research on that. And then, of course, in the past few years, and there's a lot of research on this problem. And what is it? What is it? What is the problem? The problem essentially says it learns a sequence of tasks and incrementally in a neural nets. Of course, it doesn't have to be a neural nets, but previously, when people do using SVMs, all those things, essentially they're doing a particular setting of continual learning, and in that particular setting, you can build different models.
No.
But, in the current sort of dominant sort of area of research, we want to learn all the things in a single neural net. So essentially says this neural net is our brain, for example, is our brain, and then just try to do something like humans. We continually learn and incrementally. So each task has the training data, and this is provided. But when you come to the open world, this data is not even provided. So I'm going to talk about mostly about supervised learning. And in the supervised learning, what is the task? The task essentially is a set of classes to be learned together. So of course, the set can be a single task, can be a single class, and then you basically learn incrementally one class by one class. Incremental here means in learning a new task, we don't really see the data of previous tasks. So this causes a lot of problem. So essentially say, I'm learning this new thing, I've really learned something in the past, and but now I'm sort of learning a new thing, but I don't really see the data from previous tasks. Okay. So the general challenges are basically two, and one is the catastrophic forgetting, another one is the knowledge transfer. So most of the research have been focused on this catastrophic forgetting. So the idea is also very simple, because when you learn a bunch of tasks, for example, you already learned some tasks, and which means the parameters in the neural nets is pretty much fixed for those tasks. Now you want to learn a new task. One way or another, you have to change the parameters somewhere. Okay, otherwise you can't learn this new thing. So when you change this new task, when you change the parameters to learn this new task, but you don't see the data of the previous task, and then you're going to cause some disruptions to the parameters you learned for previous task, which cause some sort of accuracy degradations for the previous task. And this is called catastrophic forgetting. And knowledge transfer is sort of trying to say, I've learned something in the past. Can I, based on the knowledge I learned in the past, to make my next task learning sort of faster or better? And so this is not much, there's not much paper on this. There's a little bit paper on this, and most of the research papers are basically on this catastrophic forgetting.
I have a question, a little one for you.
Yeah.
Don't mind. You said that this is about supervised learning.
Yes.
Is what you say also applicable to reinforcement learning?
Oh, yes. Yeah. Yeah. I'm just saying in the supervising case. Yeah.
Okay.
Yeah. In a reinforcement learning, you can also have multiple tasks. For example, you learn to play chess, and then next one you learn to play ping pong and all that kind of stuff. That's fine. Also. So I'm going to use this diagram because later I'm going to use this diagram again, just to make it more complicated. So in this case, you can see the task comes 1 to the n+1, and this is our new task. The data is provided, and then we have a continual learner, and then you have knowledge base, and hopefully you could have some knowledge from the past that can help you to learn this new task better. Okay. And then you produce a model, you go for applications, So here the tasks are given, and the task is given, and also the data set is given. Data set given. So when we come to the open world, both of them are not given. So the system has to somehow try to discover the new task and also somehow acquire the training data as well. So there are basically three popular CL settings, three settings, but two of them are popular because another one, I'm not going to talk about another one, which is a sort of a special case of this setting. So this is the setting is called task incremental learning. So it trains a separate model for each task, and the task ID is provided at test time. So this is just like you learn to play chess. Next one you learn to swim, and next one you learn to drive a car. So they're separate things. Okay, they are not. They could be related, so you can transfer knowledge among them, but they're not doing the same thing. They are doing the same thing. So, for example, in this case, I'm using the text classification as example. The first task will be learning to classify sentiment. So you basically say, I'm going to classify a product review into positive, negative, and neutral. And the task 2 is to classify relations. So, for example, the relation in the text documents. So each sentence express some kind of relation. I'm going to classify them. Another one says I'm going to extract entities from the name of the entities from the text document. So when it comes to the test time, I give you a document, and then I'm also telling you which task I want you to perform. So, for example, I'll give a product review. Normally, you want to perform sentiment classification, but of course, you can do entity extraction as well, and the classify relation too. Okay, so which means we need a task ID at the test time. Okay, what do you want? Okay, what do you want? So in terms of definition, is again we're talking about supervised learning here. Each task has the training data set, and is a number of samples, and then the main thing is this: we're learning this function. This is the input. This is the input. This is the task ID. Okay, this is the task ID, and it gives us the class. Okay, give us the class space. Okay, and so you can see here we require the input, the task ID. Okay, the task ID, because all these tasks are pretty much independent. So this problem has been solved. It's pretty much solved. What is the upper bound of this guy? So we're saying we're learning this incrementally. So we're not saying we can put them together. But if you do put them together, that becomes multitask learning. So in the multitask learning, you can share knowledge. You can help each other backward, forward, and you can help each other. But in this case, it's not clear you can help each other. But you can. Okay, you can. But it's not as easily as you do here, multitask learning. And quite a few techniques are really able to basically deal with forgetting. Okay, and that's completely forgetting free. So I'm just sort of mention two techniques. One is called HAT, and another one is the soup. The HAT basically says when I learn a task in the neural nets, I basically block it. So when I learn the second task, I set a mask on the first task. When I learn the second task, when you do backpropagation, I basically said make sure those units, those basically neurons, which is important to the previous task, are blocked. So you cannot, the gradient cannot flow backward. Okay. So essentially you're protecting what you have learned. The soup is another idea. What it does is find the subnetwork from the original network. So original network is completely sort of randomized. It's a random network. And then this guy is trying to find the network which can solve your problem. So for each task, you find a problem, you find a subnetwork. For every task, you find a subnetwork. So this is called parameter isolation because you do protecting each task. Okay. So in terms of knowledge transfer, there are really quite a few techniques which can achieve the upper bound, which is multitask learning. Multitask learning is the upper bound of TIL. Okay. The multitask learning means you learn everything together. Many tasks together, they can share knowledge. But in this case, in a TIL, this it's harder. Okay, it's harder because you don't see all the tasks together. Okay, you don't see tasks together. So what I have learned is
There's a question from Anna Maria Di Giulio,
Yeah.
but Anna Maria, please confirm if it's pertinent to where we are now. It can't be a general or distraction question.
Well, thank you. Yes, I think it's relevant. I mean, pronominal and
Then go ahead, quickly ask it.
yeah, for pronominal and aphora resolution, is it part of the tasks that are specific, right? Like sentiment analysis and things like that. So you have to, because pronominal and aphora resolution is fixed, right, in languages. You do them in a certain way. So you would have, they would fall in the set of the tasks which are sentiment analysis, right? And so on, as you said before.
I'm not sure I get your idea. So the
Okay,
task
Professor
can be
Liu is
anything.
not,
Yeah.
Professor Liu is not a linguist. Say very briefly
I'm
what
sorry,
phenomenal and aphora resolution is.
Yeah, it's did find the antecedent of pronouns. That's
Oh, okay.
the,
It doesn't matter. Here
Okay.
I'm using supervised learning, but
Okay.
it can be any task.
okay,
It
right.
doesn't matter. It can be any task. It can be
Right.
unsupervised, and
Yeah.
it can be sort of self-supervised. Okay.
Okay.
So this is the setting which is most challenging. Okay, most challenging. So this is called a class incremental learning, and this model basically this is setting produce a single model from all the tasks and classify all the classes during testing. So example is like this. So for the task one, I learned to recognize a pig and a cat, for example. So it's just like you're teaching a baby. So today I learned to pig and cat. And tomorrow you learn to probably see a sheep. And then basically tell the baby this is a sheep. And then the baby learn to recognize sheep. And then the day after tomorrow, maybe you'll see chicken and dog. And then the baby learns this thing. And then the fourth day, learns the horse and cow. So again, this is the incremental learning. Okay, when you learn horse and cow, you don't really see the data of this previous animals anymore. Okay, anymore. But at test time, I'll just give you an image. For example, this is a chicken. I don't tell you as chickens come from task number 3. Okay, just give you a chicken, and then you tell me which animal it is. Okay, which animal it is. So in this case, in terms of definition, and we still have I'm still talking about supervised learning. So we still have this data, okay, but here we don't have the T anymore. We don't have the task ID, okay, task ID anymore. So essentially, this is pretty much like what we do in learning to recognize more and more things. Okay, learn more and more things. So the difficulty with this one, obviously, the first, of course, is forgetting. So if I learn to recognize pig and cat and sheep and then chicken and dog, and then I'm going to learn horse and cow, I don't really see the data anymore. So obviously, I'm going to change the network. And change the network is going to forget what I've learned in the past, obviously. Okay. However, there's another bigger problem. Okay. The bigger problem is it's called intertask class separation. So what does that mean? It means when I learn the horse and cow, okay, and I don't see the data of pig and cat and sheep and the chicken and dog. So how can I establish the separation? How do I get a decision boundary between horse and dog and the chicken and the pig and cat or the sheep? There's no way you can do that because you don't see the data anymore. You don't see those guys' data anymore. Okay, so this is called the intertask. Among the tasks, the class separate, you cannot separate those tasks. Okay, so due to these two issues, and the class incremental accuracy are way below the upper bound. So in this case, what is the upper bound? The upper bound is the joint training. So what do you mean by joint training? Joint training means I'm learning all these guys together, okay, instead of incrementally. I'm learning all these classes, all this sort of 1, 2, 5, 6, 7 classes together. So that's the best thing we can do. So in the incremental learning, due to these two issues, and the accuracy normally is way below the joint learning upper bound. Okay, joint learning upper bound. And also because of this low accuracy, and there's practically no real life application of continual learning, pretty much no practical application. Because in practice, you always want to have high accuracy. If you you say, if I sort of learn something new, I want to get high accuracy, I'm going to get all the past data, do a retraining, to train everything together. Okay. And then obviously I will get a better accuracy. But if I don't train them together, if I have low accuracy, then for practical application, that's not good for the merchant, okay, for the application. So the theoretical question is, what is the right way to solve this problem? Okay, what is the right way to solve this problem, regardless what kind of algorithm you are using? Okay.
That was a good point for a question. Is this still now?
It's not. It's not pertinent anymore, and I check online on the original paper to get my answer.
So that question was answered. I have one anyway, and I should have asked it earlier.
Okay.
Why is the starting point supervised learning? I thought that the message of the Nature 2015 joint authored article on deep learning by Jeff Hinton and Yoshua Bengio and Jan LeCun said that the solution is to do a lot of unsupervised learning in order to buffer the kinds of problems you're raising. Is that
yeah. We're going to talk about unsupervised learning later. Okay, we'll talk about unsupervised. Okay. So essentially, if you think about the language models, they are pretty much sort of self-supervised. Sometimes you can also call them unsupervised. Okay. So what is the right way to solve this problem? Okay, to solve this problem. So the issue is you don't see the previous data, but you still want to establish the boundary, which is seemingly not possible, but it's actually kind of possible. If you do out of distribution detection. So if each of the models for each task is an out of distribution model, so means whether it's a horse or cow or something else, if I can do that, then this problem is solved. Okay, so that's essentially the idea of the theory. Yeah. So the CIL problem can be easily decomposed into basically two probabilities. Okay, so here is a classification of X. Input X belongs to the X, K, and J, and the K essentially is a task ID, and the J is the class within the task K. Okay, so is the probability is a product of these two probabilities. So this is a sort of task ID prediction. So X belongs to a particular task, and then this is the conditional probability given X belongs to this particular task, and what is the probability of X belong to a particular class of that task. Okay, so the second term is essentially the task ID prediction. So which task it belongs to. Okay, so the first task is within task prediction. So this is already given a condition of given this X belongs to this task. What is the probability of this X belong to a specific class of that task? Okay, so the theoretical result is it turns out if you want to have good CIL result, and these two are obviously they're sufficient. Okay, they're sufficient. All right. If you want to have a good CIL, you should have good WP and a good TP. But we also show they are necessary as well. Okay, they're necessary as well. And another thing is, I'm putting OOD here, is that TP and OOD bound each other, which means this, and the task ID prediction is essentially sort of correlated to the out of distribution detection. Okay, OOD is out of distribution detection of that task, So here are some theorems, and we say CIL is bounded by those two guys, and then TP and OOD detection, out of distribution detection, they bound each other. Okay, this is just some proofs, some theorem. Loss of CIL is bounded by WP and OOD detection. Okay, OOD detection. Okay. So the previous three theorems basically say they are sufficient. They are sufficient. But we also can show they are necessary. Okay, necessary as well. Okay, necessary as well. So which basically means we want to sort of achieve some kind of out of distribution detection effects when you learn each task. Okay. And then most of the out of distribution detection performs both WD and OOD detection actually. All right. And so essentially say CL requires some good OOD performance. Okay. And this is, of course, is also applicable to unsupervised learning as well. Okay, unsupervised learning as well. So, so what is the intuition? So intuition is also quite simple. It says you don't see, when you're learning something, you don't see anything in the past, you don't see anything in the future. So what can you do? Okay, so you basically say, what you can do is I can recognize myself, and also I know something is not me. Okay, so then the problem is solved. Then the problem is solved. And the solution, so the only possible solution is each task is good at OOD detection within the T-task. T-task, of course, is the number of tasks you have learned so far. Okay, so why this is T-task? Because we're talking about class incremental learning in a closed world. What do you mean by closed world in this case? Means I have learned this T-task. My classification later on the test data will only come from this T-task. They're not going to come from, basically, a priori I tell you, they only come from this T-task, not from anything beyond that. But if it goes beyond that, so for example, you can have something completely unexpected. So that becomes the open world, okay, open world sort of CIL, class incremental learning. I will talk a little bit about that later as well. And then in that case, we can make the learning completely autonomous. However, this theory did not say, only says this, you should achieve this effect, but it doesn't really doesn't tell you how to do it, okay, how to do it. Because it did not mention anything about catastrophic forgetting. It did not mention that. Okay. However, as I said previously, the TIL, task incremental learning, the TIL the problem has already been solved. Okay. So now I'll just give you a particular technique. And it's a combination of a TIL technique, which essentially deal with the forgetting completely, can solve the forgetting completely. And then each task, we're going to learn the model. That model is an out of distribution detection model. Okay, so it's not a traditional supervised learning model. It's an out of distribution detection model, means you can detect things which does not belong to you. Okay. So there's two techniques. One is called, basically it's a combination of two techniques. Both of these techniques are not our techniques. We just put them together. The HAT and the CSI and SOUP and the CSI. So this HAT is an excellent TIL technique. And the CSI is a good out of distribution detection method. Okay, it's a very strong out of distribution detection method. So if you look at the results, sort of the green parts, you can see the baselines are so way below this green parts, which is our technique. It's a combination of two things. And it's a lot better than the previous sort of the previous baselines. Right. So which basically means the theory-based sort of technique obviously does quite well. So in this case, in the first case, we do not use any pre-trained models, okay? And in the second case, we use pre-trained models, okay? We do use pre-trained models. And so this is the upper bound, non-CL And previously we called it non-CI, but normally people call it joint. Essentially, joint learning all the classes together. So this
Is this a bad moment for a question? Tell me not to.
fine, go ahead.
Yeah.
In the previous slide, you had add plus CSI, add plus sub. What was the add plus CSI plus C column that you had? Bro, I'm sorry. I mean,
You mean a CSI?
yeah, the last two. Why is that is the plus C? It's supposed to represent.
You mean plus CSI?
No, the two last rows on your table.
Two last rows, yeah. So C was basically there's a calibration, and which is basically we want to calibrate different model because this individual model are built completely independently, and then we use a little bit of data to calibrate their scores. That's all.
Okay.
Yeah. And I mean they don't really perform the best. Sometimes better, but sometimes not. So in this technique, we're still doing similar things, but we use a pre-trained model. And also we save a little bit of data from the past. We have the data from the past. So in this case, the upper bound is this row, the first row. This is the upper bound. Okay. So for this particular data set, CIFAR 10, and we can achieve pretty much sort of 92. And don't look at, there's no point to look at the AIA, just look at the last. Last means after I learned everything and I do the test. So AIA means I learn, I test, I keep learning, I keep testing. So they're basically progressively going this, incrementally training and testing. But last is the one I learned everything and then I do the test. So in this case, you can see there's a gap. There's a gap. And when you go to the, this of course means that there are 10 classes only. This is got a 100 class, so the gap has become bigger. So 82, 76, okay, and the 82, 76, and this is 72, and this is 68. And also you can see there's a gap, okay. Don't look at this red one. These red ones, they are not supposed to be correct because in this pre-trained model, in this two sort of red columns, the pre-trained model already seen the classes of these guys in the pre-training. So which is kind of cheating in a sense. Maybe it's kind of information leak. You really learned those classes in the pre-training to building the pre-trained model. And now you're saying you're going to learn this thing again. And obviously it's much easier. It's much easier. And so this one is also class incremental learning, but it's on graph. Okay, on the graph. Again, we can getting quite close to the upper bound, but this graph is it's a special problem. And this is also based on the same methodology. Okay, base methodology can achieve quite high accuracy. Okay, and now let's talk about large language models. And with the large language model, a lot of sort of this natural language processing task has been pretty much solved very well. But there's nobody tried to use large language models for continual learning. But the continual learning has some issues. Okay, has some issues. So if we have a very naive approach, and that would be sort of when you have a new task, I just keep adding, when we do in-context learning, we write prompts. Okay, the prompts we can put the training data for each class there, and then we basically say, I'll give you a test case, and then tell me which class it belongs to. Okay. So if you do a naive approach, is for each task when it comes, you just basically append the data for each class. Okay, and then you prompt your goals sort of very big. So this approach, of course, is not possible because all the large language models has a token limit. Okay, has a context limit. So it's a prompt is only can be certain lengths, certain lengths. So how do you solve this problem? There are two ways to solve this problem. One is the long context. And there are systems which does long context, but they don't really work very well. They don't work very well. I'll show some result. So what about to produce a summary? So instead of giving the prompt the original training data for each class, and I can produce a summary of those training samples for each class. But this, of course, still does not solve this token limit problem, because I mean, as you learn more classes, your summary, I mean, the number of summary, of course, is going to go very large too. Okay, we still cannot solve this problem. And so then we have a simple approach to do this. Okay, so instead of asking the system to do classification, we ask the system to produce to basically output the confidence of each test instance belongs to each class. Okay, belongs to each class. What is the confidence? Okay, so in this case, we are doing an online version of a continual learning, which is basically online CIL. Means the data comes incrementally instead of comes bunched together. Okay, bunched together. So in this case, we do incremental summarization. What does that mean is when a particular piece of data comes, and if this class, I already have a summary already, so I'm going to incrementally summarize. Okay, produce an incremental summary to cover the new data, So each class is represented as a summary that is incrementally updated as the new sample arrives. Okay, we do this online. The reason we do this online is also because when you do prompting, you don't normally give a lot of data. Okay, don't give lots of data, and but when you do offline, you have a huge amount of data to do the classification. Okay. So the test time, we have to, since we have this token limit, okay, then we're going to chunk it. Okay, so for example, for first 10 classes, I give it to the system, ask the system to tell me X, what is your confidence that X belongs to each of these classes. So this is not a classification. It just tell me what is the confidence X belongs to each of these classes. All right. So in this case, I can go through all the chunks and I got all the confidence values. And then with the confidence value, I can pick up those highest one, but of course, highest one is not good. And I pick up the top few. I can pick up the top few, and then I send those top few classes into sort of large language model. Again, I write another prompt, basically says, can you give me the classification among these top few classes? So in this case, and the system performs pretty well. Okay, so you can see here are the previous sort of baselines. So this was published in 2023, and the results are supposed to be state of the art. But when we have large language models, the results are way better. Okay, very, very good. Okay, very, very good. And we can also use fine-tuning. We can also fine-tune the models. Okay, you can fine-tune the model, essentially fine-tune the language model llama. Okay, you can get even better result. Okay, so this is like joint training. Okay, with a full data joint training. And here we only use a few examples. Okay, a few examples. It does not do so well, but when you use the full data, when we fine-tune the model, it's really good. Okay, really good. So you can see the difference between this column and all of these columns compared to the last one. And but this result, this llama, let's say the llama's result, are way better than previous baselines. Okay, the previous baselines are so much worse. So this large language model is really, really useful. Okay, you don't really have to do anything to it. You pretty much don't have to do anything to it. However, if you do something about it, you do fine-tuning about this, you get even better result. Okay, get even better result. All right. Now let's say, how do we achieve the upper bound accuracy? Okay, this is quite unexpected. So we'll try to do something else, but then end up doing this. The idea is really quite simple. So in this case, we're using a large language model. Okay, originally we're using a large language model, but of course later on we also use an image model so that we can do sort of classification of images. Okay, so that's why we call it foundation models. We only use the large language model as the feature extractor. So there's no training, no fine-tuning. Okay, we don't train the model, we don't fine-tune the model at all. Okay, just take the model as it is. So for each sample, we just obtain the features from this large foundation model. Okay, basically the hidden features from the model. So we then add some kernels to it. Okay, so in this case, we use the RBF kernel. So this is the Gaussian kernel. Okay, Gaussian kernel. What does it do? Essentially, is try to expand this feature. So this feature has a size, for example, 300, 400, whatever that is, depending on the language model you're using. And this is that number of features may not be good enough. So I'm going to expand this into a much higher dimension. Okay, so this RBF is the number of dimensions is infinite, and then we use the random Fourier features to basically approximate it, to approximate it, and we use about 5,000 features. Okay, 5,000 features. So we're not doing anything to the model itself, to the pre-trained model. Okay, the pre-trained model. So then, in training, we just computing some statistics. So for each class, we compute the mean. And for all the classes, we compute a shared covariance matrix. So all these things can be done completely incrementally. Okay, there's no need to have all the data. As your data comes in, I can compute the mean. I can also compute the shared covariance matrix. So this just means I assume all the classes have the same covariance. Yeah, same covariance. So after that, I'll just use linear discriminant analysis. This is a statistical technique for classification. Okay, this is really simple technique. It does surprisingly well. Yeah, let's see. We're using large language models in this case. So the joint fine-tuning, this is basically we have the data and then we fine-tune the language model. So this is in the past, this is supposed to be the best way to get highest accuracy for classification. Okay, when you have a large language model. So this is a few text data set, the CLINC and the banking and the DPpedia and HWU. And so you get the upper bound is 95, 91, 94, 88. This is the upper bound. So these are the sort of previous baselines, continuous learning baselines. Okay, they're pretty bad. Okay, they're pretty bad. So now with this kernel LDA, okay, we call it KLDA. You can see we can achieve, this is the kernel LDA. We can pretty much achieve the upper bound. We can achieve the upper bound. And here we have some ensemble. What do you mean by ensemble here? Because the random Fourier features, we can have random, we can have a sort of a different set of random features. Okay, 5. I think we use about 5. And then they can finally do a voting. And then we get even better than this joint training. Okay, a little bit better than joint training. So this is for the text data. Okay, text data. So this was using the BART. This is a large language model from, it's a language model from Google. Okay. However, what about the other models, other language models? Okay, so you can see for the other language models, this Mistral is 7 billion parameters, T5 is 3 billion. So you can see we pretty much can achieve that upper bound accuracy. Okay, pretty much can achieve the upper bound accuracy. And which is very surprising. Why is it surprising? Because there's some interesting assumptions here. We say the shared covariance matrix. By rather we say no. I mean, how can each class have the same covariance? Okay, which is quite interesting. Okay, and also this essentially assume the data each class is a Gaussian distribution, which is again very interesting. Why that's the case? Okay, that's the case. Maybe human beings, in our brain, we say certain classes are something like that. Okay, this is essentially probably our human beings building sort of things that are like Gaussian distributions. Okay, distributions. Okay.
Kinds of things.
Any question?
I mean, what kinds of things, human beings?
For each class. So this is a sheep, and the sheep, the class of sheep, class of boats, I would say, all these things, they essentially is a Gaussian distribution. Okay, it's a Gaussian distribution. And then we also do this using image data set. Okay, image data set. Of course, the image data set, the models, the pre-trained models are not as good as the language models. Okay, obviously, language model. We use the Dino 2. Dino, this is from Meta, from the Facebook. Okay, again, we use a bunch of data set. You can see we pretty much can achieve most of those things that are sort of upper bound, except one thing. Okay, this is a tiny image net. That's about 3% of difference. Yeah, about 2% something difference. Right, and which is could be one of the reasons it could be, you know, the language model are much better than this image models, language models. So the upper bound, we can pretty much achieve the upper bound. I mean, the 2-3% is not terribly bad. Okay, and also we have not tried to improve this. We probably want to, we probably can improve this to make it sort of really match the upper bound. Okay, really match the upper bound. Okay, and this Dino is a unsupervised model. So normally called a self-supervised model. So it's not a supervised model. Okay, so previously I used this data set was a supervised model. Okay, this was a supervised model. Okay, that's why it can have information leaks, because you are really learning those classes. Okay, you really learn those classes in the pre-training stage. All right, but in the Dino case, and you don't see the classes at the pre-training stage. It's a self-supervised training. It's done basically on a large amount of image data. Okay. So which is quite interesting. If you think about this, and you can see this was the previous slides, and there was, you can see the gap here between the first line 95-92 and 82-76. You can see the gap. You can see the gap. So it's about 6% of gap difference. But when you see here, it's pretty much no gap. Pretty much no gap. All right. So which made me think about this particular problem. Okay, so I'm going to make some possibly controversial statement. Okay, so what is the implication? The implication is, you know, does this imply something about a human brain? Okay, does it imply something about human brain? All right. So, for example, do humans learn representations? Do humans learn features at all? Okay. So, for example, on the right-hand side, I have an apple and a banana. Okay. When we see these two guys, do we learn any features from these two guys? My answer is probably we don't. We see the full image of this guy. We can, I mean, our brain already has the capability of extracting possibly everything about the banana, for example. So when we learn to recognize these two things, we don't really learn features at all. Okay, so for example, when the mother teaches a baby to recognize apple and banana, okay, what is the mother doing? The mother is basically telling the baby, this is an apple and this is a banana, just telling the baby the name of these two objects. Baby already know they are not the same thing. Okay, so this is completely different from supervised learning. Supervised learning means you're going to find the difference, right? You're going to, you know, to see what is the difference between these two guys, and you go to learn a lot of features. You go through neural nets, many levels. You learn lots of features, and then finally you're going to classify this into the apple and the banana. So based on our previous result, we think humans, we have the inbuilt, quote unquote, large foundation models. And after maybe a few years old, we pretty much don't learn representations. All the representations is already fixed in our brain. Okay, so I'm not sure this is true or not. Okay, this is true or not. But I think
this already. Can I ask now? Is this what you just said now? Is this the gist of why deep learning prevailed? Because in the lower ranks, you just unsupervised swallow everything.
Yeah. Yes.
So it's the same principle.
Yeah, unsupervised, which is basically unsupervised things are already. I'm not sure whether people was sort of inbuilt with these things. Of course, in the millions of years of evolution, and then we already learned all these features. And now we don't really learn features at all, I believe. Okay, so it's not like the neural nets now. We give the input, and the image with pixels, and then you learn many levels, sort of going through many levels and learn the final representation, then you classify. Okay. So which means the objects has an internal representation which is pretty much stable or constant and is independent of tasks it's involved in. So when you see a banana, whether you classify the banana against the apple or against sort of a pear or anything else, the banana is banana. So the representation is fixed. Okay. So you don't really learn banana features. Okay. So which basically means with the language model or whatever model, that word model, whatever model you call it, the pre-trained model, and the downstream task, we don't learn any features. That's what I believe. Okay, based on the result I have over there. So the training of large language models or the foundation models is just like emulating millions of years of evolution. Essentially, it's unsupervised, pretty much. Okay, and I don't know whether this is true. I think possibly this is true. So we need to build language models. Okay, so AI is so basically based on this, I think the AI, the most important task is still training or building a good foundation model or world model. So everything else is just secondary. Okay, so you work on everything else, it's not that interesting because later if you have that models and whatever you have been doing probably will be completely wasting of time. And that's pretty much the case for many natural language tasks. And for example, previously I do sentiment analysis. Yeah. But now, previously, of course, we built our own classification models and multiple levels, different architectures to classify the text documents, product reviews, whatever, into positive, negative, and neutral. But now, if you don't really need to do anything. You just ask ChatGPT to tell me, is this sentence positive or negative? The guy can tell you much more accurately than our previous trained models. So everything we did in the past, sort of meaningless. Yeah, pretty much meaningless. All right.
If you follow your analogy with evolution, I have two things to ask about that. You sort of say that the autoencoding was done by the evolution already.
Yes.
But what about even in the specific case of Google Images? The reason that Google Images got so good was because it didn't get a prepared package. It had to do the autoencoding itself, right? From the huge database.
Yeah.
With large language models, you also have a large database, but it's words.
Yes. Yeah. Yeah. So that's why I'm saying this large language model or foundational image or language is like emulating millions of years of evolution. I mean, it's not exactly, I don't know whether exactly, but it's trying to do that. Somehow it's trying to do that.
This is supposed to be implication, so I need to know. You say this is an implication. What is the implication of this implication?
The implication of our result here.
I understood that. I understood with how it is that Mama tells the apple, and then you've got millions of years behind you to help you out.
Yeah.
But what does that in turn imply? What is the implication of that?
What is the implication? Implication is the last sentence. AI's most important task is training foundation models. Everything else is secondary. We should build world models.
But foundation models, we have also large language models which are dealing with words. But
Yeah.
those words are connected to that evolution history that you're talking about, but not as words.
Yeah. I'm not saying what we're doing now is correct. Okay. I'm not saying that the current way of building models is correct, but it's just, we should be building this kind of models, foundation models. What is the way to build it? I don't know. I mean, the current way, obviously, I'm personally, I don't think it's correct way of doing it. I mean, it's obviously not the same thing as our brain, how brain works. That's what I think. But if building this foundation world model is basically trying to build our basic brain. Okay, so everything else we learn afterwards, after we have this basic brain, we don't learn any features. We already have all the representation inside.
To classify cancer cells and non-cancer cells. We don't have an evolutionary past of looking at histological slides to distinguish cancer from non-cancer. So it has to be something else.
Yeah, but the cancer cell and the non-cancer cell, that representation is constant. They are the same. They have a sort of the representation is fixed. Whether you are going to classify this cancer and non-cancer cell, that's basically in our case was basically a linear layer.
When you say it's fixed, do you mean what it looks like to the
Yes.
eye is fixed? Is that what you're
Its
referring to?
internal representation is fixed.
Well, I don't know what that is.
You see, when you learn the language model, I'm sorry, when you sort of learn to classify cancer cells, non-cancer cells, right? So you go through many layers of sort of neurons, right? Neural nets, layers of neural networks. And then you learn the feature representation. Final layer, let's call it the feature representation. Right? You learn the representations. Right? So you use multiple layers of neural networks to learn the representations. Correct?
Okay, we have a question here.
Yeah.
Speak loud and clearly.
Sure. Yeah, thank you, Professor Liu. Actually, in regards of your example of we have the representation all within, I think you refer to what is referred usually as a source grounding, because to come back to the example of banana, there's different kind of bananas, and as human we get the experience to taste it, not just see it, but to touch it, to feel it, and so don't you think that the grounding when it comes to human is way more has way more dimensions that
Yeah. I agree with you completely. Yes. That's why we say we need to build world models. I'm not saying the current models are correct. The current way of building those world models are correct. I'm just saying we should focus on building that model. So that grounded model will be obviously the best. But if we just look at this as a picture, okay, we don't really touch it, we don't really eat it, I think the representation in our brain is constant. It's already fixed. We don't learn any features. Not like traditional classification. You give me an apple, you give me a banana, you give me a bunch of apple, a bunch of banana, and then I start to go to multiple layers, going through many layers and change the weights or everything in order to get my final representation, right? That's neural nets is doing learning representations. But what I'm saying here is that all those things are really built in. We don't learn representations. As humans, we don't learn representations. It's already built in.
We don't. We're humans, and we don't just learn from looking, smelling, tasting, feeling. Okay, there's a question.
In terms of second language, what do you think if we learning second language, we should learn how to present by features?
No. The second language, you're essentially doing some kind of a mapping, right? From your first language to your second language, right? You're not learning any representations.
In each language, there are a lot of nuances we should learn by features.
Yeah. But those nuances is already in your brain. You're not learning those nuances. You are just recognize this.
What about new things that comes to the world like COVID? We didn't have experience of that, and it like jump and evolve. So we should learn the features.
Like what? Like what?
COVID. The question is COVID. All of the things that were learned about COVID since COVID came.
COVID is just a name. COVID is just a name.
All right, what's this? The trick, the Hungarian trick for vaccines.
Those are just
that we learn how actually deal with these things, new normals by learning features of it, and then we adopt ourselves to it.
I don't think we learn features. I don't think we learn features. We learn just mappings. Those features are already in your brain.
Okay, so we do features upon the mapping, maybe.
Yeah, you use words. For example, language. You're matching those things in your brain with some words. You're doing that mapping.
Okay, there's several questions. Did you have one as well?
Yeah, yes. Thank you, Professor, for your presentation. And I have one technical question, maybe. What do you mean by confidence in one of the slides related to continual learning, please? And if we talk about feature extractor also, is it can we say that continual learning on foundation models are maybe distribution on learning, let's say, or not?
This technique does not. This is basically in context learning. You write prompts. You only write prompts. We don't touch anything about language models.
And what about confidence? I don't get this.
So the confidence is so. For example, I give you two examples. I say this class documents has two documents. This is let's say politics. I give you the basically two examples, two politics documents. I give you another class which is sports. I give another training document, two sports documents. Then I give a test document, give to the language model. I say, for this test document, and what is your confidence this document belongs to sports or belongs to politics?
When you said chunks, for example, in this kind of learning, I believe it's really a distributed data set. It's really based distribution, but we have not the idea of feature selection here, feature extraction.
No.
I can't get it.
So this is just when you use ChatGPT. Yeah. You use ChatGPT, you just writing prompts.
Yeah, I know.
You just writing prompts. When you writing prompts, normally what you do is you do classification. You give let's say you give a class, you give two examples, which are training data basically, and then another class two training data, and then you give a test data. Say, which class does this test documents belongs to? Right. That's normally how you do it. When you do a classification with in context learning, which is writing prompts. But here we're just trying to say you can't do this for continual learning, because if you need to learn lots of classes. So you're going to have lots of training data, right? So that's hit the limit of token limit. So the prompt has a limit. You cannot be longer than that limit. So
Two questions. Oh, sorry, were you going to continue?
Okay, thank you.
We have two questions, but I want to make sure you asked first, but are you, is it following this string or are you going to take it somewhere else?
Following this question.
You're following. Yeah, okay, so you get it.
In hyperdimension, like when we are narrowing down the classification by classes, like freezing, how would you explain it? Like we do it by features, we do it by having low accuracy. How we're gonna?
There's no features here. There's no features here. It's just writing prompts.
Okay, so how are we gonna limit ourselves?
The ChatGPT will tell you, what is ChatGPT's confidence of this document belongs to that class. Yeah, writing prompts. Yeah. So, I mean, how does ChatGPT do it internally? That's another matter.
Okay, go ahead.
Yeah, I had a question about where exactly for you is the delimitation between what a feature is for the real world when you're doing the possible meaning of that, and what is just a mapping. Like, let's take the banana for example, for some features that naturally don't get in classification chance. Like a kid learns that banana is going to ripen and go and smush over time, like learning the concept of depth of fruit or the feeling of touch. Is that that's just mapping another concept to it?
Yeah. That's a different modality, right? Different modality. I'm just talking, in this case, I'm just talking about the perception. The eye sees it, right? Later on, you touch it, you taste it, you hold it. I mean, you get a lot of attachment of different aspects of the banana.
So we're pretty much treating features like, let's say, another representation of a universal grammar for the person. Pretty much, the brain pretty much know everything in advance. He's just learning how to map everything.
I basically say it was just language mapping to some representation in your brain. That's it.
Yeah.
Okay. Yeah, it's very provocative, what you're saying.
Yeah, that's why I say it's controversial, but that's my belief.
Okay.
Because of this result, make me feel it's something like that. I can achieve. There's no forgetting, no nothing. Just using the models, just give me the representation of that thing. And
we still have time, so I'll get back to this, but let Anna Maria ask you a question and we'll get back to this.
Okay.
Yeah.
Thank you. Thank you, Professor Bing, for the nice talk. I want to ask you, where does the representation come from? Is what we have in our brain a recursive function that generates representations? And if so, what are the evidence that we have from brain studies that it's
there are some brain studies about this too. There are some sort of neuroscience studies. Basically, they say the representation is stable. It's pretty much stable. They call it stable. Here I call it constant, but they call it stable. The representation is stable. So the same thing, if you see this time, you see in different contexts, they call it stable.
So a related question, how about, which is also related to the previous question, what about variation?
Variation, that's essentially the covariance matrix, right?
Okay.
Yeah. So essentially, that's my conjecture is in our brain, all the different classes, types, categories, they are basically a Gaussian distribution of representations.
So would that extend to syntax of human language? Or just for categories?
No, just for categories. Syntax is a sequence of things. Yeah,
well, depends what you think it is. Maybe it's a representation of some sort too,
Yes,
it's not string linear, but it's a representation.
Yeah, but that's not the basic representation.
Yes,
It's actually the language level things. Yeah.
yeah. So for concepts, for words, for concepts of
Yeah.
words
Yeah.
that they have inside, this
Yeah.
would be the model.
Right.
Yeah. All right. Thank you.
Other questions here? We
Okay.
still have time. Unusually, we have a time. Was there something you wanted to add formally? I have more questions, but you didn't finish your entire.
I only have a few, two, 3 slides to go.
Go ahead.
Okay, let me go ahead. So, so what will be the next level of continual learning is just open world. So previously we say we learn so many tasks, we only classify so many tasks. We only classify so many classes. We assume there's nothing else. But in this case, in the open world, and we will have something unexpected, definitely. Okay, well, there'll be new things. Okay, and that is called CIL plus. We call it CIL plus. And my machine is not moving. I don't know what's going on.
You have to touch it with your mouse. That's it.
Yeah. Okay. So in the open world, we also want to detect things which are unexpected, so novel. Sometimes we call it novelty. Sometimes we call it out of distribution, okay, out of distribution detections. Okay. And the theoretical result of the CIL we just described is also applicable to CIL plus, almost, not completely. Okay, because previously we have a T bounded the out of distribution within the task T, but in this CIL plus, and we are going beyond that, which means there's no bound. So anything new, we should be able to detect it. Okay, it will be detected. So if we can detect it, which basically means we have a new task to learn. Okay, and then can we make this system completely autonomous? Okay, so which basically means you have a new task, but you also have to acquire the training data in order to learn. Okay, so can we make an agent to do all these things by the agent itself? Okay, so here is an example. So it's a greeting bot in a hotel, for example. Let's say there's a robot roaming around in the lobby of the hotel, and basically have a small talk with guests. All right. For example, you see an existing guest, say, "Hello, John, how are you today?" Okay. So this is a sort of existing guest, and the robot can recognize this person. All right. But what happens if it's a new guest? Okay, it's a new guest. Okay. Then the system must recognize he's new. The person is new. Right. So this is out of distribution detection. And this is also create a new task. Create a new task. For example, the bot could say, "Welcome to our hotel. What's your name, sir?" Okay. And then what this sentence is doing is try to get in the class labels. Okay. And the guy says David. Okay. Then got the class label David. Okay, got David. And then the bot can sort of take some pictures of this person and then incrementally learn to recognize this person, David. All right. And when you take a picture, you can take not just one picture, you possibly can take multiple pictures. And that's basically the continuous learning part. Okay. So next time when the bot see David, you can say, "Hello, David, how are you today?" Okay. So you can see this whole process completely autonomous. So the bot does not need a human engineers. Okay. Does not need people to label data, all those things. But it does get the people to label the data. But this is very natural, right? You just ask, you just have a chat with this person. I got all this data. So can we achieve this in the future for robots? Okay. Of course, in this case, we're talking about a person, but obviously we can talk about anything. Okay. So anything you can detect, this is unknown, and then obviously you cannot just depend on the bot cannot depend on itself, because a lot of things you have to align with humans. So you have to talk to human. What is this? Okay, is this a tiger or is it whatever? Right? You always have a name for that thing, and that's humans give it a name. The bot cannot give it a random name. Okay, random name. So you always have to have a sort of interaction with humans, and in the process, you gain a lot of knowledge. You gain the training data, everything, and then you learn incrementally. But of course, this is a very, very complicated task. In a real hotel, the situation is much more complex. How do you know the bot is a new guest? Okay, it could be another person. How do you know is that even a person? Is that animal? Is that furniture? What is it? Because you don't really know what that thing is. So that means you need to characterize it. Okay, you have to characterize it. So different categorization requires different responses. And so for example, if this thing looks like an animal, then you probably want to report to the hotel staff. If it looks like a hotel guest with luggage, all these things. And then you can just say, welcome to my hotel, what's your name, sir? All right. So characterization essentially is trying to sort of getting some attributes from this unknown object. Okay, unknown object. If you're a self-driving car, which is also quite obvious, for example, in front there's the obstacle, there's something in front. I mean, you want to know, is this guy moving or is a sort of a still object? If the guy is a moving object, which direction is moving? So that basically tells you how do you respond, how do you accommodate. Okay, and then at the same time, you can also continually learn. Okay, continue to learn to become more and more sort of knowledgeable. Okay, so you can see the previous diagram has only this part, and this part. But with this open world, and we got lots of more components. Okay, so for this part of the model, you need to detect novelty. Okay, not just classify the existing classes. So when you detect novelty, you also have to have relevance. If you detect something novel, maybe it's not relevant to your task, so you probably forget about it. You don't learn it. And then you have to characterize it. And then you have to adapt to that situation. And you also have to do risk assessment because that thing is unknown. And then you need to be careful. And for example, in self-driving car, it's very important. You want to assess the risk, whether you're going to hit that thing or not, or this kind of stuff. And then you have the interaction with the user. And when you detect the new objects, you have a new task. Okay, new object, you got a new task. And also you have the ground truth because you already see the object, for example. So that you get the ground truth training data from that. And then this becomes a closed loop. So the system, you can do this, it becomes autonomous. So this is basically the future of robots. We want the system to learn by itself. Instead of keep sort of labeling a large amount of data to learn to recognize every small things. Okay, everything. Yeah. So this is pretty much I want to say. Just to summarize. So the foundation models are critical for not just for continual learning, but for normal learning as well. And with this, we're talking about the catastrophic forgetting or about this inter-task separation. There's no such a problem. Okay, so if you have this foundation model as a feature extractor, this problem will disappear. Because you're not changing the model. You're not changing the model. Okay, the basic model you're not changing. So I believe human is probably like that. Okay, like that. And then we can achieve the upper bound. And of course, this two techniques we talk about, the summarization technique and also the mean and covariance, the LDA. They basically follow the theory as well, because in this case, a summary basically tell whether you belong to this class or not belong to this class, depending on distance. Okay, the correlation and the mean essentially give you a Gaussian distribution. Okay, and then you know what is close to you, what is not close to you. Okay, what is not close to you in terms of individual classes. Okay, so what is all these things I want to say is the downstream task means beyond the foundation models should not learn representations. I mean, this is a very controversial statement. Okay, so we should all focus on building the foundation models. Okay, essentially the basic brain. Okay, basic brain. So those things are done. Now lots of problems are very easy to solve. Okay, so the future work. I mean, of course, in my own research, I've been trying to work on this open world kind of case to make the agent to learn completely autonomously. I think that's pretty much what I want to say. That's this conference with lifelong learning, and also thank you very much.
Thank you very much. It was an excellent and provocative talk. Even though I personally think you're wrong, I find it extremely interesting and informative. What you're essentially saying, correct me if I'm wrong, is that lifelong learning for human is trivial because evolution has done it all.
I think so.
Well, that's very controversial to say that. But all right, let's switch away from the human. We know that humans can have large language models because humans talk. But there are other species who also categorize and who don't talk. So there's nothing to place the word.
I mean, nothing to do with talk or not talk. Talk is just a label, right? It's just a label things.
Well, just a label thing. If we weren't talking, like we're also communicating.
The monkey does not know. In monkey's brain also. I mean, monkey doesn't have a word of trees or something like that. But monkey has no problem, right?
Well, I agree that monkeys and rats and lizards have categories. They don't name them and they don't talk about them, but they have categories.
Yes.
And they have evolution. So whatever it is that evolution did for us, or for us before we began to have language, it does for them as well.
Yeah, it's just they have not developed this high level of intelligence with the languages, all these things.
Well, there are many implications there. What I want to tell you, though, is that one of the features of language, Anna Maria, I don't know if you think of this mostly syntactically. I think of it, it's much more interesting semantically than syntactically. But we have an infinity of propositions that we can form, subject predicate statements, using the content words and also the function words that we have, right? Are you saying that Darwin anticipated everything that we have, could, or will say, except for some trivial lifelong stuff?
No. My statement just say we don't learn representations. All the representation is really fixed. You see, whatever things we can see, they can be represented in our brain. We don't need to learn anything.
What do you mean by represent?
So in this case, the representation is just let's say this picture of banana. I don't know what's the representation in the brain, but obviously we have a representation of this banana in the brain.
Yeah, but I don't know I know what an image, a visual image of a banana is.
Yeah.
Okay, but is that your model for what a representation is? A visual image of a banana?
Just from a visual perspective. I mean, if I see this banana in my brain, that's a representation of the brain. This representation is not learned. It's not like a multiple level of neural nets. I do back propagation and change weights of the thing. No.
Okay.
Just go forward. Just go forward. And this representation is there.
Anna Maria.
Yes, thank you. Coming back to what you said before about the semantics, I find that there is a difference here between what is called distributional semantics, going back to Harris, where you look at the words and their distribution, with compositional semantics, where you have the representation and you compute the semantics based on the semantic of their parts, and their, sorry about the word, but syntactic relations, right? So maybe in the evolution, just, you know, maybe the human part comes from the recursive function that allows representation over which applies compositional semantics. So of course, it's not the neural net, and I think that there's questionable, as you mentioned in this talk, neural nets and all these things around it, the many calculations and things like that. You know, after all, you know, children, they learn language quite fast, right? They don't do a lot of calculation. So maybe what you present is very, very nice and important. And there is also this other aspect of representation that are generated on which the structure upon which the representation are, in a sense, interpreted by the human mind as difference from birds or, you know, or other animals of the, you know.
Sure. I mean, we don't really know what the bird sees, but I mean, maybe just see the color or whatever.
Yeah, no, but there's a lot of studies, you know, on whether bird songs have grammar, and in fact, there are very much dialects on that, on the birds singing properties, but they lack the, for example, center embedding properties and higher levels in you know, human capacity in doing language. So, but I think that, you know, things like you can think of WordNet, like some kind of relation between words, but the theory behind WordNet is very limited. I think that what you presented is much more interesting because it's with representation which are basic, right? And very little calculation about synset and things of that sort. So I thank you for that. But my point is that there's a lot of work to be done.
Obviously.
On machine learning and, you know, whatever, automation, which deals about human intelligence, being able to speak and produce meaning as we do.
Which requires grounding, I believe. I mean, it's just what's that grounding, right? How do you do it? That's very, very tough.
Thank you.
On that question, it's time to end. So I will just tell you that we enjoyed your talk very much. We learned a lot from you. And whether we agree or don't agree, we've profited a great deal from what you had to say. Thank you.
Thank you.